Next section is on stacks. Thanks to Mark Clement and BYU for a lot of this material. So our learning objectives are, hopefully after completing this, you should be able to explain how subroutines are implemented in machine code, describe what makes a subroutine cohesive and loosely coupled, and why these are desirable. Give examples of what might be found in an activation record. Explain caller and callee safe subroutines. Describe how the stack is used in recursive functions. Explain how global and local variables are implemented. Explain how the stack is used by the interrupt service routines. So our topics are the stack, subroutines, subroutine linkage, saving registers, stack operations, activation records, recursive subroutines, and interrupt stack usage. The first little mini lecture here that we're about to go to is just on the stack. So let's look at some terms. Activation record. Basically, these are parameters activated on the stack by a subroutine call. Callee safe subroutines. Subroutine saves the registers used, so that means the callee doesn't have to worry about it. The subroutine itself saves any registers, all the registers that anybody could possibly use. The caller safe subroutines, the caller has to save the registers, and the caller only has to save the ones he knows are needing to be saved. So you would perhaps save less. You wouldn't use as much stack space to do that. An interrupt is an asynchronous subroutine call. That means it could happen at any time. LIFO, that stands for last in, first out. In other words, it's a stack. A stack is a kind of a data structure. Loosely coupled, that means all parameters are passed as arguments. Pop, well, that means removing the top element from the stack. Push means putting an element on top of the stack. The stack is a last in, first out abstract data type structure. The stack pointer is an address that points to the stack, where the stack is right now. Points to what's known as the top of the stack. Strong cohesion. Subroutines that performs just one task as an example of strong cohesion. A subroutine is a synchronous task or unit. So let's look at stacks. Stacks are the fundamental data structure of computers today. A stack is a last in, first out, or LIFO, abstract data structure. A true stack is a restricted data structure with two fundamental operations, namely push and pop. Elements are removed from a stack in the reverse order of their addition. In other words, if they were popped in 1, 2, 3, 4, it would be 4, 3, 2, 1, getting them back out. Kind of like you would on a stack. You know, when you stack papers on top of each other and then you want to go back down, you have to bring the top one off first, which is the most recent one you put on there. Memory stacks are used for random access of local variables. So let's look at some stuff that's specific to the MSP430 stack. The hardware support for the stack, register R1 is known as the stack pointer, and the stack pointer is initialized to the highest address in available RAM. Like in the MSP430G2553, that's 0x0400. In the MSP40F2274, it's 0x0600. And in the ARA processor, the MSP430F5529, it's the 0x4400. And you can notice that our processor has 10K bytes of RAM available, and the others have significantly less. The stack actually grows down towards lower memory. So as the stack gets piled under, it's actually piling under. It really is. It's what goes. It's not what goes on top. It goes underneath, and it keeps using up the RAM from the high address, and it's going down toward the low address. So you initialize the stack pointer at the beginning of the program. Here's a little bit of an assembly program to do that. They make a label stack, and they equate that to, or a variable stack, they equate that to 0x 600 hex there. And then they have a label at the beginning of their thing. First thing they do is they move that 600 into the stack pointer, which is register 1. And you can see over here on the right the memory map of the MSP 430F2274. So the MSP 430 stack is a word structure. In other words, every time you advance the stack pointer, it goes a whole 16 bits. It goes 2 bytes. The least significant byte of the stack pointer is always 0. That's because it's a word structure. The stack pointer points to the last word added to the stack, or the top of the stack, TOS, sometimes they label it. The stack pointer is used by the following operations. These are assembly instructions. A push instruction, it puts a value on the stack. A pop instruction pops the value off the stack. A call instruction pushes the return address on the stack. And an RET instruction pops a return address off the stack. And an RETI instruction pops the return address and status register off the stack. And that's because you needed to save the status register, because interrupts, when you go off on an interrupt, that could happen at any time, and you don't want to lose the status of where you were when you go back there and start re-executing things. So interrupts, like I said, they push a return address and the status register on the stack. That's why the RETI needs to pop them off. So up or down, it's a little bit tricky to look at this. This is the way the MSP 430 stack works, and may work the way many of them work. You could have it go backwards from this, but generally what happens is the stack starts at the highest RAM location and grows down toward 0 in RAM. And let's just see how that works here. So here's the memory address 0, and there's the memory address FFFF. So if you just listed, started at 0 and started writing memory down, in that case, the stack actually would grow up. But the way we kind of normally visualize it is over here on the right. We have 0 at the bottom and FFFF at the top. And the stack starts somewhere in the middle at the beginning of RAM, and it grows down toward 0 as you add more and more stuff on it. It gets bigger by growing down. So look at that on the right. This is important. It says, unlike a coin stack, the memory stack does not move the data in memory, just the pointer to the top of the stack, which decrements towards 0 as the stack fills up. So we have a quiz here. Let's see if you can figure out what's in the stack and where the stack pointer is pointing in the following cases.